It's my pleasure to give a talk today, this is a joint work with my colleague Zhang Hao, and my title is From the Littlewood-Paley-Stein Inequality to the Burkholder-Gundy Inequality. This is a problem about the classical Littlewood-Paley-Stein inequality. So I should first introduce the symmetric diffusion subgroup. This definition can be found in Stein's book in 1970 in his book Topics in Harmonic Analysis, Littlewood-Paley theory. This is the definition. Let omega a mu be a sigma finite Meyer space, and t to small t is bigger than 0 is called a symmetric diffusion subgroup on omega if t to sub t satisfies the following 6 conditions. The condition A says that t to the sub t is a contraction on every LP. The condition B is the semigroup property for t to the sub t. The condition C means that the mutation from when t goes to 0, the t of sub t f goes to f in L2 for every f in L2. The condition D means that t of sub t is positive. That means the t of sub t is positive, preserving that. That is to say, if every f is positive, then t to the sub tf is positive. The condition E means that t to the sub t is self-adjoint on L2. This is also why this kind of semigroup means symmetric diffusion semigroup. The condition is the symmetric. The condition F is the Markovian property. In Stein's book, he shows that every diffusion semigroup is analytic. So we can define in a sexual. So we can define the Littlewood-Paley G-function on LP defined as this form. Stein proves LP boundedness of Littlewood-Paley G-function operator. In his book, he showed that for every p bigger than 1 and less than infinity, there exist 2 positive constants, I say LPT and SPT, such that the left side is the LP norm of f minus ff. Here f is the projection from LP onto the fixed point subspace of t to the sub t of LP omega. I will explain why the left side is of this form later, and the right side it means that the LP norm of g to the power t f is less than SPT times the LP norm of f. Stein proves the above inequality by virtue of Burkholder-Gundy's martingale inequality via Rotha's dilation theorem and complex interpolation. He first shows the right hand side, and then by duality he gets the left side. You can from the definition of g of power tf say that the fixed point of t to the power t of LPF doesn't influence the value of g to the power tf. So that's why the left side has a f minus the projection. But Stein's proof doesn't give the optimal orders of the constants LPT and SPT. Last year, if we consider the corresponding problem for the subordinated Poisson semigroup P to the sub T, This is the definition. This is the definition. We know that the subordinated Poisson semigroup is also a symmetric diffusion semigroup. In 2021, she developed the proof of Stein theory on the Littlewood-Paley-Stein inequality. I used the holomorphic calculus to get some of the optimal order of the constants in the Littlewood-Paley-Stein inequality. The LPP is the corresponding constants in the Littlewood-Paley-Stein inequality. I go back to the inequality. That means since the subordinated Poisson semigroup is also a symmetric diffusion semigroup, so the semigroup PT also satisfies this inequality, and the corresponding constants satisfies these two estimates. That means LPP is less than the maximum of P and P prime, the square root of P prime, and SPP less than the maximum of square of P and P prime. Here P prime is the conjugate of P. That means P 1 over P plus 1 over P prime equals to 1. Moreover, the estimate above the constant SPP is optimal as P goes to 1 and P goes to infinity. But the corresponding problem for the left hand side constants LPP was left open. This problem is divided into two sub-problems. Is that its estimate LPP is less than P when optimal as P go to infinity, and find the optimal order of LPP as P goes to 1. We find approach to solve the problem A, but the problem B is left open. Now. We use an idea developed by Nouveau that established a profound link between the martingale theory and the ergodic theory. He shows that the Dub's maximal inequality for martingale can be obtained by Danforth-Schwarz maximal ergodic theorem. We will prove the analogous result for the square function. Here, square function is the Littlewood-Paley G-function for convenience. This result implies a pointwise equivalent relation between martingale square function and the Littlewood-Paley G-function. And we can obtain the desired result from the optimal order of the Burkholder-Gundy's inequality. We will see it later. We give the definition of martingale square function. Let omega a mu be a fixed probability space, and n less than or equal to 0 be a filtration of sigma subalgebras. For a random variable f in L1, we defined we said the conditional expectation and the martingale difference, where we denote E0 is 0 as convention. The square function of the martingale ENF is defined as SF. It's the square root of the square sum of the martingale difference DENF. Now we go to our special diffusion semigroup. Give a strictly increasing sequence AN with A0 is 0 and AN goes to 1 when n goes to infinity. Define the operator T is the sum of an minus an minus 1 times En. Denoted by T of power T, the operator obtained by continuous functional calculus. Then for T is bigger than 0, T of power T can be written as this form. From this form, we can check that whether T of power T satisfies the 6 conditions of symmetric diffusion semigroup. This is what we will do later. We can see that T of power T is the exact symmetric diffusion semigroup. Then if we take some special coefficients An, we can calculate the Littlewood-Paley G-function and compare the Littlewood-Paley G-function and the martingale square function. We can know that for example, if we take An as this special sequence, then the Littlewood-Paley G-function of f associated with the special diffusion semigroup T of power T, then we get this pointwise equivalence. Since T of power T is also a symmetric diffusion semigroup, so we can obtain Burkholder-Gundy's inequality from the Littlewood-Paley-Stein inequality. That means if we have Littlewood-Paley-Stein inequality and T of power T is a symmetric diffusion semigroup, we apply Littlewood-Paley-Stein inequality to this semigroup. We get the Burkholder-Gundy's martingale's inequality. Recall that the Burkholder-Gandy's inequality is when P is bigger than 1 and less than 0, P star denotes the maximum of P and P prime. Then we have the LP norm of F is less than the constant times the LP norm of SF and bigger than the constant times LP norm of SF. Here I remark that since we just use the fact that when P goes to infinity, the constant P minus 1 is best possible when P goes to infinity, means the right hand side when P minus 1 is best possible. And when P goes to 1, the left-hand side is best possible when P goes to 1. So it's an immediate corollary that for any diffusion semigroup T to the sub T, and for P bigger than 2, then we have the LP norm of F change minus F, the projection is less than P times the LP norm of Littlewood-Paley G-function. And P is the optimal order of LPT. Since we know that from Xu's result that LPT is less than here. Since LPT is less than LPP is less than P and LPT is bigger than P. So we get that the optimal order of LPP is just P. This result also gives the optimal order of LPP, and the best constant of SPP also when P goes to 1. Next, I will give a sketch of our proof. First, we should verify that the semigroup we defined before the T of power T is the exact symmetric diffusion semigroup. We rewrite T as the sum of 1 minus a n minus 1 times the martingale difference den. Then by continuous functional calculus and the fact that dep times dq is 0 for p not equal to pq, we obtain that T of power t is of this form. Then since we choose that an is increasing, so the coefficients is positive. And the conditional expectation is also a positive contraction. So T of power t is also a positive contraction for every t and for every LP. Since En is also symmetric, so T of power t is also symmetric. And since An goes to 1 when n goes to infinity, so T of power t is Markovian. Notice that the L2 norm of Tf is the sum of coefficients times the L2 norm of martingale difference, and the L2 norm of F is the sum of L2 norm of martingale difference. So T is injective on L2. And by a lemma that if S is positive injective continuous operator on a Hilbert space, then for any x in H, we have this result. When t goes to 0, the norm of t of power t x minus x goes to 0. This lemma gives the fact that the T of power t satisfies the condition C. That is the limitation condition. And by definition of T of power t, we know that T of power t is a positive contraction on every LP and Markovian and self-adjoint. So we verify that T of power t is exact symmetric diffusion semigroup. Then what we need to do is to verify that to get the pointwise equivalence. Since that any f in LP can be approximated by a sequence of Fn on LP, restricted on every sigma subalgebra An, we can add F just in this restricted LP space. And in this case, T of power Tf is a finite sum. And we can calculate the Littlewood-Paley G-function of such F. This is a quadratic form, and Aij is the log 1 minus Ai minus 1 times log 1 minus Aj minus 1 over the square of log 1 minus Ai minus 1 times 1 minus Aj minus 1. This is a symmetric matrix. What we need to do is to find an appropriate sequence An such that the eigenvalue of such a matrix Aij has a universal upper bound and a universal lower bound. We know that we can let the Aij has great, the difference of Aij has great gap. Then the matrix is measured by his diagonal elements. For example, we choose An is 1 minus e to the power minus 16 to the power n plus 1. And A0 is 0. We get the desired result. And this pointwise equivalence can also be extended to the vector valued case and non-commutative case if we can well define the vector valued martingale and non-commutative martingales. For the vector valued setting, if x is a Banach space, and P is bigger than 1. PQ is bigger and less than or equal to than 1 and less than infinity. For an x-valued LP martingale ENF, we can define the corresponding Q variant of the martingale square function for Q bigger or equal to 1 less than infinity as the SQF. As we just use the x norm of DENF, and we use the power Q in place the absolute value and the square. And define for Q bigger or equal to 1, we define the Q variant Littlewood-Paley G-function as we also use the x norm and power Q to in place the absolute value. In this case, the proof of this case is similar to the classical case, but there is a little. It is a little different since we can't use the quadratic form to control the eigenvalue of the matrix. So we use some, and we can also get this result, but we should use another trick. Notice that this integral is from 0 to infinity. If we so we have 0 to infinity. This integral is bigger than from 0 to constant m, and we divide the integral and from 0 to m to very small intervals, and t0 is m, tn goes to 0. The idea is same as the classical case. We let the difference Tn and Tn plus 1 is very big. So the integral on each small interval can be measured by just one term of the t of power t. So we get this pointwise equivalence on the vector valued case. For the non-commutative setting, we first should define the non-commutative conditional expectation and the non-commutative martingales. Let M denotes a finite von Neumann algebra equipped with a normal faithful normalizer trace tau, and M to the sub n increasing filtration of von Neumann subalgebras of M, whose union is weak star dense in M. And En is the unique normal faithful conditional expectation from M onto Mn such that tau En is preserve the trace. This result can be moreover En extends to a contractive projection from LPM onto LPM, and for every p bigger or equal to 1 and less than infinity. Non-commutative martingale with respect to this such a filtration, Mn is a sequence that x we denote x, then x equals to xn in L1 such that xn equals to En x n plus 1 for every n bigger than 1. Denote dxn is the martingale difference, and we also denote xn is 0 by convention. define the column and the row square functions respectively for x in L1M. And the difference is the dxn and the dxn stars. Respected to the row column and the row square function, we can define the column and the row Littlewood-Paley G-function. Let T, first we should define the non-commutative symmetric diffusion semigroup. Let T2 sub T be a semigroup of operators on M. We say that T2 sub T is a non-commutative symmetric diffusion semigroup if it satisfies the following conditions. The condition A is every T to the sub T is unital, normal, and completely positive. The condition B is for any x in M, T to the power Tx goes to x in the weak star topology of M when T goes to 0. This is the analog condition of the classical case. And each T to the sub T is self-adjoint in the trace. The condition D is the extension of each T to the sub T from LPM to LPM for every P bigger or equal than 0 and less than infinity is completely contractive. These results are the some analog of the classical case. Then it is well known that such a semigroup extends to a semigroup of contractions on LPM for any P bigger or equal than 1 and less than infinity. So we can define the analog Littlewood-Paley G-function, the column and the row. The difference is also the T to the power T and T to the power T x star. We can define the operator analogously and the symmetric diffusion semigroup analogously. That T of power T is also this form. Note that F is E1, the projection is E1. Then we can choose an appropriate sequence AN just like before. We also get this pointwise equivalence. The proof of the vector valued case, the non-commutative case is just analog to the classical case, so I omitted the details. Thank you.
Are there questions or remarks, comments? Yes,
the non-commutative case, it's for any finite or semi-finite?
Our result under the finite case, but it can be extended to the semi-finite case, I think.
I have also one question. Can you go back, I think, one slide? So for where you have the concrete example, I was just wondering the choice of the numbers, an 1 minus e to the 16 to the n plus 1.
Yeah.
Is there some, so this means that the factors in your expansion are 1 minus an, so they are e to the minus 16 to the n plus 1, so they go to 0 very fast.
Yeah.
Is that the reason why you chose that form?
Yes. The idea of the vector value is also this: when we choose a sequence goes to 0 very, very fast, so that the Littlewood-Paley G-function can be, since the operator can be written as a sum of the den of such a coefficient, and when the coefficient has great distance, then the Littlewood-Paley G-function of t to the power t can be the other term can be measured by the appropriate den. It means that I will go back to the classical case. It's here.
So it's the sum of the t times log.
Yeah. When this term has great gap, that means this matrix, the diagonal elements is very big and the other term are very small.
Okay, that's very close to the diagonal.
So we can use the result of dyadic form, the quadratic form to transform the Littlewood-Paley G-function to the martingale square function.
Thank you.